Good evening, everyone. A very warm welcome to this lecture. Today, we have with us Professor Konard, who is an IEEE Signal Processing Society's distinguished lecturer for this year. Professor Konard received master's degree from Technical University Poland in 1980 and PhD degree from McGill University, Montreal, Canada in 1984. He joined INRS Telecommunications Montreal as a postdoctoral fellow and since 1992 worked as a faculty member. Since 2000, he has been on faculty at Boston University. He is an IEEE fellow and a recipient of several IEEE and EURASIP Best Paper Awards. He has been actively engaged in the IEEE Signal Processing Society as a member of various boards and technical committees, as well as an organizer of conferences. He has also been on the editorial boards of various EURASIP journals. His research interests include video processing and computer vision, stereoscopic and 3D imaging and displays, visual sensor networks, human-computer interfaces, and cybersecurity. We are extremely delighted to host Professor Konard here for a talk, and we thank you, sir, for visiting us. And over to Professor Konard for the talk. Thank you.
Thank you very much for the introduction. It's always awkward to hear about oneself, these accolades and all this stuff. Thank you for inviting me to India. I received this email one day, okay, I'm a distinguished lecturer and invite me to India. Oh, that's far. But we managed to figure out all the logistical details, and I'm happy to be here. And so far, I'm enjoying it enormously. Food and sights and metro. It's far better than in Boston. It's like 10 times better metro than in Boston, so I really enjoy it. So thank you for inviting me. I'm going to, I don't know, my lecture is a bit maybe long, I'll try to skip some things, but I'm going to talk about privacy preserving localization and basic recognition of human activities, and I'll try to make it into 45 minutes. If I'm too long, I'll skip some stuff. So let me first say a few words about Boston University. Probably most of you are not familiar with the place. Maybe some of you are. Motivate my work, I'll talk a little bit about localization, about recognition, and also I try to squeeze in maybe localization by modulated light, which is kind of an interesting topic we recently pursued, and then I'll give some final thoughts. So first, BU is a private school, private institution. In the US, you have to live in the US for long enough to understand that the University of California, Berkeley is, for example, public, and yet Stanford is private. And you go by names, and it's kind of difficult. It took us 10 years probably to figure it all out. In Canada, where you have a PhD, everything is public, basically. So it's a private institution. We are about 35,000 students. It's a kind of range. Interestingly, half are grad and half are undergrads. So there's a significant grad population. You can see about 4,000 faculty. Schools and colleges from medicine through business, through law, through engineering, all possible majors. We are located basically in downtown Boston, not downtown, outskirts of downtown Boston. This is kind of the main focal point of the campus, Marsh Plaza. And we are squeezed between Charles River. On the other side is this school you may have heard of, MIT and Harvard. And we are on the other side of the river. And there's overall, it's kind of always interesting to say that Boston area has 60 colleges. By colleges, I mean universities and colleges. MIT, Harvard, Northeastern, BU, Tufts, University of Massachusetts, and smaller ones you never heard of. Anybody who's ever heard of Wellesley College? It's a small liberal arts school, but very famous people, like Hillary Clinton.
Is that Wellesley?
Wellesley. It's a town in the suburbs, and it's a small college, but very kind of, I would say, narrow in liberal arts, but it has a lot of very famous alumni. So there's like 60 colleges. Now, we are kind of on the river, almost in downtown Boston. And our department is located in the photonics building, which is this big building here. And we are about 50 faculty, about over 400 undergrads, 200 masters, and about 150 PhD students. So total is, I'd say 800 out of these 150 PhD students, typically 2 to 3 per faculty member. BU is not well known for Hillary Clintons, but we have 2 graduates, or not maybe not graduates, 2 people associated with university at some point in their lives. And the one on the right probably you recognize, Martin Luther King. He did a PhD, not undergrad, but PhD in BU. But the guy on the left, you would say, yeah, like any guy in the 19th century, you know, looks distinguished, probably some scientist or something like that, right? He was a faculty member for 3 years only. Anybody can venture a guess who the person is? I always say that if BU was smart enough and to patent his inventions, it would be the richest university in the world. Totally. Easy. It's Alexander Graham Bell. He was faculty member for 3 years. In that time, he invented telephone. He went on and we never benefited from that. So a little plaque in the corner.
So interestingly, we have one faculty member who is graduated from CS department.
Really? Oh, great. Who is this?
David Vera is theory.
Do you know who? Maybe did PhD with? Doesn't it? Okay, great. So another person, all right, great. So our department is focusing on a few research areas, and I'll just list them quickly. We are very strong in photonics and nano. In fact, the building was funded for photonics, so we have a lot of clean labs, white stuff, and lasers, and all kinds of things. A lot of hardware, very expensive. We have been very rapidly growing in mobile, cloud, and cybersecurity. We're hiring a lot of people in this area. Imaging and optical science, we recently kind of converged between photonics and optical sciences in order to develop new methodologies, and we have intersection of this with data science and intelligence systems, with signal processing, phase, computer vision, all the data science stuff. And we have a very strong connection to our medical campus and our biomedical engineering department, which is very highly ranked in the US. So we have a lot of bio and medical EC kind of activity in our department. I am part of something group called Information Data Sciences, which basically spans these activities in these 3 areas. Now, this project has been basically collaboration of myself with Professor Prakash Ishwar, whom I've worked for a number of years, and it's an outgrowth of our collaboration, and our former PhD students who only went on graduating, went to work somewhere, and recent masters and undergrads. So overall, the support for this was from NSF and Boston University for undergraduates, and overall, all my travels and my talks are funded by Signal Processing Society and Distinguished Lecture Program, so I thank them for facilitating my travels. So let me start with a paradigm shift. So back in the early 20th century, what happened was that moving assembly line made manufacturing of American automobiles, first application, not very easy, but easy compared to before. And then it took probably almost 100 years, and then full automation happened and robots, and today people really physically participate in car manufacturing much lower percentage. Now today we are kind of observing another paradigm shift, and is it going to take 100 years? I don't know, but we've been all in this situation probably, right? Those who drive and drive daily like myself, coming at night at 7 p.m. dark, and I'm booked after a whole day of teaching or doing research, sit and you don't know where you are. So we are going towards, autonomous driving. I don't know, I found it online. Is it going to happen in 10, 20 years, 30? We don't know. It's happening right now a little bit with varied consequences. With Tesla and the accidents. We don't know, we are there, but this is just a part of it. Now, something happened 100 years ago, electrical lighting, going from kerosene and fire. And it took about 100 years until we went to LED, and LED has happened everywhere. I know Prakash educated me that he loves fluorescent light, which I totally hate, because I was raised in Poland where it was incandescent light, and he was raised in India where it's fluorescent. So we have completely different views on which light is nice. To me, yellow is nice, for me, white is nice. Anyway, that happened in around 2000, LEDs. The question is, LEDs were pushed so much by industry as an energy savings measure. And we posed a question about 10 years ago, is it only energy? Is there anything else? And LEDs are a bit better than fluorescents, but not that much. Fluorescents are only extremely efficient in terms of energy. So we asked, is there any other opportunity that one can exploit from LEDs beyond energy? And today is kind of starting another paradigm shift where LEDs are commonly used, they illuminate the space, you can actually even control the spectrum. Philips bulbs, you can actually, from an app on the phone, you can control the spectrum of the light and so on. All this is nice and beautiful. The question is there anything else? Can we better exploit this opportunity? Is LED, can it do more than that? And we had a large, it's something called ERC, Engineering Research Center, which is a multi-year, 10-year grant from NSF given to multiple universities. That's $37 million over 10 years, many industrial partners, 3 universities. Where we are trying to answer various questions related to LED. Is it LED going to be that interesting? And this is a long motivation for my work. I'm going to talk in detail soon. So the questions we asked were, number one, energy savings. Yes, they're obvious because LED uses less energy. Secondly, can we somehow leverage sensing where we could activate light whenever needed? Not always, but when needed and where needed. And that was obvious, you know, when you walk through corridors in some hotels, it just turns on as you walk. That's easy stuff. But we asked other questions, and this is not my work, but I'll just report on it quickly. For example, can spectrum of LED be shaped to improve performance? Performance in what sense? For example, you're watching some TV or some movies. You can shape the spectrum. It's optimized from a human visual system, so you can better perceive the light on the screen. Another thing is, it's been used quite a bit in our collaboration with the University of New Mexico for circadian rhythm. As you take a flight from here to US or to Europe, your sleep pattern is disturbed. It turns out that with spectral shaping of the light, you can recover much quicker. Some people take melatonin. Experiments were done also with LED lighting. Can it improve somehow? And that's been done by people in the University of New Mexico. However, where I participated in this research was mostly in productivity gains. This was the third question. Energy savings, how benefits, and productivity savings. And what I mean by that is the fact that LED, unlike incandescent, old-fashioned light bulb, or fluorescent, can be switched on very quickly, on and on, in the range of hundreds of kilohertz, even megahertz. And this being beyond the fusion limit of the human visual system, you cannot perceive it. And yet it switches all the time. Can we steer it and beam data? And that was part of my colleague's research, Professor Little's, where the idea is something you may have heard of, visible light communication. So it's not through EMF, it's through light, it's a visible light. So it's what we see, but because it's done at high frequency, we cannot see the flicker. It looks like a continuous light, and yet data is transmitted. And in fact, in some experiments, very early experiments, in very laboratory environment, distance of a couple of meters, perfectly collimated beam, shooting at the receiver, data can be transmitted up to 1 gigabit per second for light. One key question is, or key point is, it must be a line of sight. Because it's visible light, you cannot obstruct it with anything. Wi-Fi is beautiful, because you can go behind a wall, unless it's LED. You can go, and you can still receive the signal. With visible light, must be direct line of sight. But, point is that we have lights all above us in the rooms. Can we use, if we replace this with LEDs, can we beam the data to our, not maybe phones in the, that's money, in the pocket, but if I remove the phone, I want to read my email, stream video, I can stream it directly to the phone, or to a laptop, or to a tablet. The question is, if my
lightning serves as the transmitter, simply through light. And I can transmit easily to a fixed device, like a picture frame, or let's say a TV on the wall. But what if I want to stream to something that a person is holding in a hand, and the person is moving in a room? Then I need the line of sight. I cannot beam from the device behind me, I need to beam from the device in front of me. So what I need to know where the person is, what is the body orientation of a person, because usually we don't hold the phones behind our backs. And thirdly, what type of activity, because it might be useful to know that I'm working on a laptop or doing something. So localization, orientation, and type of activity, and this can be used also for other applications like lighting control, HVAC control, even robotics. Now, all this is clear. The point is that this has been done, localization, recognition of activities, has been studied for years. It's not a new topic. I'm not reinventing the wheel. And excellent performance has been accomplished if you use cameras. But sometimes we don't like to use cameras. This is kind of supposed to be funny, it's a little smile picture, but the point is that often we do not want to be recognized. And many people look at the camera and say, I don't want to be in the field of the camera. Sometimes you go in public and take a picture, somebody says, no, don't take a picture of me. And this is respecting somebody's privacy, and there's some applications where you don't want to be recognized. So what people had proposed in the past was to use reversible methods. You could scramble the data. You could scramble the image and transmit it, and then unscramble it. But it turns out that in a long time was shown that it's vulnerable to attacks. You can unscramble and find out the original image. Then people have done data encryption, even with sophisticated methods. But very recently, even without knowing the keys, people have done unscrambling using deep learning. Of course, deep learning does many things, and this is one of the applications. So this is not, again, very safe. What people have also looked is at irreversible methods. Irreversible methods where you actually modify the data, that you cannot go back to the original data. And some of the work was done before acquisition. So basically, a lens of a camera is modified in a way that it accepts certain display mask, and it takes original image that would have been captured by the sensor, imposed on this a mask from the optics, and combines produces a different image. And a system of recognition of the human face would actually fail with this, and it's been shown that it actually works reasonably well. The difficulty is that it's very coarse control of the optics. You have to modify the optics every time in order to be able to multiply the target face of the display lens. Some other people have done cartooning, where they take original image or video and they cartoon it digitally. However, it's still possible to eavesdrop, because the cartooning is happening after CMOS or CCD, after the data is acquired and before it's being transmitted, and you have to modify the data. So if somebody hacks into the system, can still get before and get the data. So it's good, but it's not perfect. So here's all this motivation. So here's what we pose as a question. I know we can see, maybe you cannot, because you're recording, right? All right, so hopefully it will work, okay. So what we ask as a question is, can you use ultra low resolution data? This is somebody wavy with color. This is a low resolution black and white image. This is a 10 by 10 pixel black and white, 3 by 3 pixel. This is a single pixel, literally average data out of this. And this is data not action. And the question we're asking is the following. Well, can we localize people or recognize what they're doing from such low resolution data? Not from this data, from this data. And that's what we set out to do and say, is it possible at all? If it were possible, what would be the benefits? If my sensor literally captures this data or this data, I can literally put it on YouTube, and I don't care, right? If I can use utility from this, telling where the person is or what the person is doing, you gotta recognize the person from these images. And secondly, side benefit is that it's at such a low resolution of the data that the bandwidth is very low. So you require very little transmission bandwidth and very little processing. You can do it little on Arduino. So these are benefits. The question is it possible at all? And that's what we set out to do. Let me talk about the first topic. So person localization. So the idea is I want to know where the person is, because otherwise I wouldn't, without knowing the person, I would beam from this transmitter and I wouldn't be able to reach the, let's say, the target. So with cameras, easy. We ask the question, is it possible to replace cameras with single pixel sensors? So every camera literally captures one value at one time instant. And we built a testbed where we actually had an area of about 2.5 by 2.5 meters, where we placed on a scaffolding, we placed single pixel sensors, a specific sensors from a company called Chaos AMS. It's a bit not true that it's a single, there's actually 4 little subpixels with different color filters, RGB, but we're averaging everything and using only one value. And we have 6 of those. Of course, we are going to use a data-driven machine learning type of approach. So we need to have ground truth. How do we do it? Well, we use the Hollywood trick. We have, in addition to our system, we have a set of 12 cameras with IR lighting, and we're using little markers on the body, which actually the system can figure out exactly the position of the marker with the precision to a couple of millimeters. So in training, we basically put a hat with a little marker, and the person walks in the field of view of those cameras. We can record precisely the position, and simultaneously we record from our sensors. We have 6, instead I'm showing only 4. We record the value at every sensor readout, and this is a position in the 2-dimensional space. And we keep doing that, and this is our readings, this is ground truth, and we can train an algorithm. And we're not doing anything really fancy, something very simple. We are going to use basically a SVM. And we have treated this as 2 different problems. It's a regression problem, it's a classification problem. So in classification problem, we are trying to decide in which of those 9 boxes the person actually is. And we're doing this very simply 3 by 3 division into cells. Each cell is a class basically, and then we are doing simple SVM with our BFR. And alternative to this, we are using SVM as a regressor, and in this case, we are trying to find continuous coordinates of the person. Nothing fancy, rather simple. We are doing 2 separate SVM regressors for X and Y. Okay, so as a data set, we have recorded a number of random walks of people, and we have used this our system to get ground truth. So we have divided our experiments into 2 settings, a public setting. Public means that this is like a, let's say, conference room like this, of course much smaller, where a person coming in is not known to the system. So we have a bunch of people we train on, but we allow a person new to come in who was never part of the training. So this is a public scenario where new people may come in. It's a more difficult scenario. So new users appear quite often. System cannot be trained on all users because we don't know all the users. So we basically leave one person out cross-validation. So you're removing a person, testing another person. Right? And in public setting, we can do CCR, which is correct classification rate, which is basically telling how often we are hitting proper box. And it's about 2 out of 3. Remember, we are using 6 single pixel sensors only. And in terms of the fine localization, meaning exactly the regressor, we are doing about 35 centimeters out of 2.5 meters. So within the distance, like with this box, within probably a foot, you can tell where we are, more or less. And in the private setting, sure.
So, in terms of information, when we say single pixel, so what sort of information is captured?
Okay, just one single value. It's the AD converter on the output of the chip produces values in, I believe, 16 bits. So we are obtaining 16 bits at every, and it's running, I believe, 10 hertz. So it's 10 values in a second, and we have 6 sensors. So we are capturing 60 values out of 6 sensors in 1 second.
Okay. And what do we think would be the difference when a person say enters the room and versus the room is vacant? What would be the difference in information used to?
Between,
Let's say a room is vacant,
yes,
so there is some information captured.
yes, background.
Yeah, background.
Right.
And when the person enters, so some other information is captured.
Yes, so the person walking in occludes. For example, if I walk in, I will occlude this bright part, and this will change the reading of the sensors. And this is what being captured. So if, for example, the background would be exactly the same color as I am,
Okay.
I would be camouflaged, right? But as soon as I move, probably will be other colors in the background. So me occluding parts of the environment causes the signal variation, and that's what we are capturing.
And we need 6 cameras at least, or?
No, we just used 6 because we have 6 sensors.
Okay, we
And
can
we
still
actually-
do away with 1.
Good, I'll show the results on this in a second. We actually also used 4, I'm not reporting because I wanted to shorten the talk. But yes, we tried 4 as well. But I'll show you some results in a second.
So in this setting, so in this setting, are you assuming 1 person at a time? or
Yes,
everybody?
correct. We're assuming that this is 1 person at a time. Yes. So we also use in private setting where we assume that this is like a home, where everybody is a family member, and therefore we can train on everybody. Of course, our particular walk is in the training, is not part of the testing, but still is the same person. Yes?
Are you controlling for movement of any other object in the environment?
We are assuming it's static.
Okay,
So
no chairs
true-
moving, no tablecloths moving?
Correct. So if I were to move a desk or a chair, it would change the environment, we would have to train again. But the idea was really fundamental. Is it, before that we didn't think, single pixel, I can't get anything out of that, right? So we're asking, is there information in it? And we believe there is. You're asking very valid questions. Multiple people, how do we approach that? What if you move the furniture? What if you paint the walls? You have to retrain. And this is, we haven't answered those questions. But ask the very basic question. Normally you use 3 cameras, HD, fantastic, you can do everything with that, right? Can you do it with much lower resolutions? So, of course, in this case of private setting, we are doing a little bit better. Not surprising, because we train in people who actually participate in the testing. Okay, here's a demo. So here a red means an estimate and blue means a ground truth. So we were running in this case a ground truth from actually from Kinect, that doesn't matter. And the red one is estimate from single pixel sensors. And this is done it wasn't done in real time. We collected the data, processed in MATLAB, and then we displayed it. But it does reasonably well. It doesn't really do perfectly. And of course, if we move the furniture, if we change lighting, if we do other things, of course it will not work as well. But to us it was surprising that just from 6 measurements every moment, we are getting reasonable precision. So literally from these kind of measurements, we are getting the 6 measurements like that, we are getting this kind of quality of result. Now, so this is localization. So we said, interesting, single pixels. If we use multiple pixels, it could be even better perhaps. But then we moved on and we started thinking, okay, can we recognize activity? So now I know the person more or less is under severe constraints. I admit that. But now, can I recognize the fact that the person is doing something? And can we do it with very low resolution? So people have done a lot of work on this low resolution, on the order of 30 pixels, 30, 40 pixels, and they get very good results. But we said, okay, can we even go lower into the range of teens or even maybe a few pixels by few pixels? And the difficulty was that while we had this panel sensor, single pixel, available to us, I cannot easily go online and buy a 2x2 pixel sensor and 3x3 and 4x4 and 10x10. It does not exist. Nobody manufactures them. So we said, how do we approach even the problem? So we said, okay, let's start with simulation. And if we simulate the problem, we'll be able to control all aspects of our environment. So we used Kinect 2, which is this not structured light but time-of-flight Kinect camera with relatively high resolution of the depth field. And we used Unity 3D, I don't know, this is a game development engine. Lots of games have been developed in Unity 3D. And this is free, available, and we just said, okay, we'll emulate a room in Unity 3D, and we will
be able to have a three-dimensional scene of a room, let's say. We will select some avatars, and we'll animate avatars by actual human motion captured by Kinect. Like in Hollywood, you know, you've seen Avatar movie probably, and all the motion of is human motion, whereas the texture mapping is completely synthetic. So we decided to do that. We have generated an environment with 5 cameras and this kind of a room. We have captured individual behavior by basically using Kinect, where, for example, this is isolating a phone. And this is an RGB image, this is a depth, and this is a skeleton obtained from SDK from Kinect. So this data is given to us by courtesy of Microsoft. And knowing this, we can right now take an avatar, use the skeletal to drive the motion of an avatar, and we can, in a room, place cameras with different resolutions, different orientations, because we have full control over these cameras in the synthetic, in the Unity 3D environment. Okay, so here is an example of a person avatar raising an arm at arbitrary resolution from arbitrary camera angle. So we can completely emulate the environment, whereas building a system with 5 cameras, 3x3 sensors, I just don't know where to go to buy. I can go to Amazon and look for 3x3 sensors. Nobody makes them. So this allows us to do it. We can capture different resolutions, different locations of cameras, angles of cameras, whatever we want to do. So this is, for example, captured at a resolution of 10 by 10 pixels through simulations. Okay, so here we had 12 subjects, 7 male, 5 female. We used avatars for all of them. We have 9 actions, typical like in a conference room scenario. Yes?
So how was the downsampling done? Is it just standard?
We emulated in the Unity 3D a camera that only captures the light. So basically, there's a lens. We can model the lens, and the lens averages a particular sector. It looks at, averages the light, and produces an image pixel. We did not capture high-resolution images, and then we could decimate them, standard signal processing. But we modeled the camera in Unity 3D. And we assume, again, single avatar in field of view. So it's not in multiple people, one single avatar in the field of view. So these are typical actions we have considered. And because we are going to test very low resolutions, we cannot have elaborate features. We're talking like 2x2 or 3x3 or 5x5 pixels. So we use very simply grayscale of value readout at every location. We do some mean variance equalization in order to compensate for variety of clothing, because people have different clothing, avatars have different clothing, which basically is a non-causal processing, but that we haven't dealt with yet. And we used a very simple classifier of nearest neighbor. We didn't go for anything fancy. For us, it was really to see, can we somehow use low resolutions? You could improve the results with better classifiers. But can we somehow recognize activities with very simple classifier from low resolutions? That was the key question. So our results were that at 10 by 10 pixels, using all 5 cameras running at 30 Hertz, among 9 different actions, with 12 subjects, we're getting about 90% the correct classification rate. At low frame rates, so also 10 by 10, but only 2 Hertz, it drops a little bit. Not surprising, because some actions are faster, and you're not capturing all the motion because of low frame rate. If you go to one camera only at 10 by 10, 30 Hertz, you're dropping 2, because you're seeing one viewpoint. So if you're raising an arm like this, camera's behind you, not very good. Then if you go to low spatial resolution, only single pixel, but 5 cameras, you're getting dropping. And if you go to everything low, single pixel, 1 camera, 2 Hertz, you're getting 50%. But remember, we are talking about 9 actions. So what's the random toss? 11% roughly. So it's doing better than random toss, but not good. So yeah, go ahead.
Seems like dropping the sampling rate has a more effect than the number of pixels in this case.
I would not claim, based on this experiment, that this is a general conclusion. A good observation, but we haven't done enough variety of experiments to be able to claim that.
But one could also argue for the frequency range in which the human motions are observed, and I think at some point you're going below that. So 2 Hz is clearly human motions, around 12.5 Hz is what's observed, and so if you were to get something, you have to go for accommodating for Nyquist, you have to go till 50 Hz. So 30 Hz is still crossing 25, which is twice it, but 2 Hz is clearly low.
I totally agree, and this could be optimized, and especially if you were talking like sports events or something like that, you would probably need to go to faster. If you look at hockey games, right, you need to have much higher frame rate because the motion of the players and, let's say, hockey is different, right? I agree. We didn't try to optimize it. For us, it was like a fundamental. Can it work at all?
I have another question.
Yeah.
So I'm not sure if you are going to show a confusion matrix of some sort afterwards, but was there a trade-off observed between the type of activity that you took in your reference task list and the resolution at which you were capturing the information? And I'll give you a specific example for why that question comes to mind is you have motions where I believe if I were to divide the frame into, let's say, a grid of 3 cross 3, and maybe you have a higher resolution than 10 cross 10, you could see the body crossing certain grid lines and going and moving in. Because every task requires at least one body part, either the whole upper body or the hand crossing certain things, right? But if I were to just be waving my hand, which could be possibly in a single grid location on top right, would you be possibly not be able to capture that at all, right?
Yes, I agree.
Yeah.
We didn't try to engineer it for the best performance for a specific scenario. And I admit this scenario is the video conference scenario, in a sense, because this was part of this larger grant, where other partners were working on video conferencing systems. And we participated by saying, well, can we recognize from this low resolution? You could definitely optimize it. And we stopped at some point, we didn't go any further. And I would not even put too much faith into those numbers, because we didn't do extensive experiments. For us, the fact was that if we do go to low resolution, lower frame rate, fewer cameras, it's going to drop. I mean, there's no question, right? There's less data. We like a lot of it. We like big data. This is small data. We like it with very little data, right? If I can go on, no need for high frame rate, only in the context of these actions. The moment you have different actions, you may need to go for higher frame. And if you want to recognize action maybe like this, you need higher resolution. Not much will help you 3x3. But it was for exploration more for us. So then we said, okay, this is all synthetic, always Unity 3D, no noise, no illumination variations, nothing. It is a beautiful scenario, and we are happy with the result. Well, we need to be kind of in a real world a little bit more. So what we decided was to test on real data set. And one of them that we really found was useful was something called Exynos ROI. It was an old data set from action recognition, which later on was extracted as subsets, smaller resolution, from which we even downsampled further to get very low resolution. But this is real data with real noise, with real illumination variations. It's not synthetic. So we use that, again, 12 actions, 10 subjects, slightly different actions. So we can compare really numbers. And then we tried the same thing, looking at the high everything and then going to lower frame rate, lower resolution, lower number of cameras. And without going through the numbers exactly, roughly we said, okay, about 7 to 10% drop compared to the previous results. When you have real data, real noise, real illumination issues. Still, one single subject in the field of view of a camera. Okay, 10% reasonable. We are about 80s in optimal conditions. Okay, so this is reasonable. We said, not bad. Now, can we really make it work in a real system? So now we are back to, we cannot build 3x3 sensors. We don't have expertise for that, we cannot buy it, so we go back to single pixel sensor. We use 12 single pixel sensors. They are placed around the screen, like would be here, 12 single pixel sensors. All data is harvested from those sensors, and it's not done in real time, it was recorded and then processed. We didn't have a real time, but it was done in MATLAB. I'm saying real time, but I think it was not real time. I'm maybe cheating here. I don't remember right now exactly. But it was done in MATLAB, or maybe it was real time. I don't remember right now. So you will see this student. He will be doing, again, it's a conference room scenario. So he's in front of the screen and he's trying to do three things. He's walking, like I'm walking in front of the screen, so recognize that. Second action he's doing it because it's part of a bigger project. We wanted to control the lighting, so he's going to do that. Recognize the hand motion up so that you turn on the lights. And then he's going to point to the screen. Recognize this. This was a demo for NSF. NSF was coming to see us, what are the products of our work. So from synthesized environment to real data to real working system, we try to demonstrate. So it will show what he's doing with the delay. So the system is recognizing he's walking very slowly, and that's the demo effect. If you do something, in real time, those of you who work with hardware and demos, you know that whenever you need to do the demo, it doesn't work. So we are very slowly walking and trying to make it work. Then he was pointing, and I think, sorry, maybe I did it too quickly, I was talking. So he will walk first, then he will raise his arms, and the lights will, some delay will switch on. And then he will point to the screen, and it's going to be recognized as pointing. So it's a delay because the system is not that fast. So we are quite happy that we get 12 single pixel measurements at about 10 Hertz, and he was able to recognize. And of course, the data is literally, you can think of 12 waveforms. You want me? I can put 12 pixels, 3 by 4, put it on YouTube, and literally I can walk naked, and nobody will see anything because it's single measurements at single time. So it was kind of interesting to us. Now, so this is second was action recognition, and we didn't explore it in any depth. It was more kind of, can it be done at all? And then we decided, okay, the third thing we need is not only to know where a person is, what the person is doing, but what's the body orientation, because I want to beam the data from the LED to my receiver, all being held at some orientation. So if I'm facing this way, this light and this light, I can beam the data. That would be occluded data by my body. So we need to know the orientation. So where's this tablet? So we didn't find extensive data sets on whole body orientation, but we decided to use as a proxy head orientation to see how our methods work. And basically, traditional methods work with full resolution, and our question was, can we, from this kind of resolution data, can we get orientation of the head? And we have tried to do a couple of methods, and this work is 3 years ago. We did deep learning, and anyway, deep learning on extreme low resolutions. We didn't know even where to go with that at the time. This is literally 5 by 5, 3 by 3 pixels, which we could have done with deep learning. We didn't do it. And we used something standard to those who work in computer vision, HOG, Histogram of oriented gradients. It's a standard method, and it works reasonably well at high resolution. It doesn't work at very low resolutions. So we looked at another feature, which is basically just the partial derivatives plus magnitude and angle of the gradient. And we built feature vectors out of that, and we have used standard support vector regression, SDN again, standard, nothing fancy, and try to see, can we estimate the angle of the head with that. And here I'm putting a big table, but I'll summarize it quickly. So this is 10 by 10 resolution, this is 5 by 5, and this is 3 by 3. Top is HOG, and bottom is our gradient-based feature. So we see that at 10 by 10, SDR with HOG works a bit better than our gradient-based feature. But at low resolutions, 5 by 5, 3 by 3, the gradient-based feature works a little bit better. Now these are little details, we didn't explore it much. The key point was that at about 10 by 10, we are getting error in pitch, roll, and yaw, each independently, each angle. We are getting an error of about 10 degrees. So really, within about this much, we can tell what's the angle. Is it good enough if I have a body oriented this way, about this much angle? It's good enough to tell me that I can look at these transmitters to beam and not definitely at those. And at lower resolutions, it would be a bit worse, 11 and even 13 degrees, which is still within the reason. What is interesting is that at full resolution, at the time, I'm talking about 3 years ago, at the time, the state-of-the-art method for the head orientation recognition was about 5 degrees at 640 by 480. And we are talking about twice as bad at 5 by 5. So whether I have 5 degree or 10 degree, I can still tell which light to beam the data to my receiver. So that was encouraging to us, and he said, okay, this is interesting. Now how much time I should be finishing. I'll only give you an idea. I won't go through all the math because there's too much to talk about this. But it's interesting that in all the methods so far in localization, we made one key assumption. In addition to one person and fixed environment, one key assumption was that illumination wasn't changing. It's a fixed illumination. But what happens if I train the algorithm, I collect the data for training in one lighting conditions, and then I test in a different lighting conditions? That happens commonly because of lights being turned off and turned on, because of windows being in a room, and during the time of the day, you get different lighting. This is a very serious problem. So we decided, in this case, with passive light, we simply pick up light directly from the light source or bouncing off the walls and ambient light, and we are basically measuring what happens in the room. But ambient light will change, it will destroy this accuracy. So we said, well, what's the distinguishing feature of LED? Well, LED can not only transmit data, but it can modulate at high frequency, above 60 Hertz, imperceptible to human eye, but it can generate different patterns from different LEDs. And through that, you can leverage this to provide robustness to illumination changes. How? And I won't go deeply into that. This was work started a few years ago by one of our partners in that large ERC, Professor Kevin Boyer, who worked on something called the light transport matrix. Let me explain quickly. If I have several light sources and several sensors, every light source produces light flux, which bounces off in the room and is collected light by a sensor. And I have multiple of them, multiple light sources and multiple sensors. And I can construct a matrix, basically, of sensors versus light sources that tells me about the environment. If I introduce a new object into this environment, this will be disturbed somehow. And from this disturbance, I can measure where this disturbance happened. So disturbance caused change in the light transport matrix, and by minimizing certain error, I can find out where it happened. And this would take another 20 minutes to explain, but I'll quickly only explain one thing, is that light source J produces a flux, intensity flux, that bounces off, let's say, a floor. We assume that there's no walls for simplicity, and it reaches the sensor. And this amount of light flux, light intensity, multiplied through the light transport matrix is the amount of light that reaches the sensor. And there's another light source, of course, so we need to sum over light sources. Over light sources producing the light sums up to a single sensor. But there's also ambient light. We need to add it, and this constitutes the readout from the sensor. Now, how do we compensate for this ambient light? Okay, so I can write this previous expression in a matrix form. It's intensity times how much light is transferred to the sensor, plus ambient illumination. This is the readout of the sensor. But if I go through all the light sources and all the sensors, I can construct a linear matrix equation. Now, I can express this as this expression. And now, what if I provide a slight perturbation? Some of the lights are slightly perturbed, have a higher brightness or lower brightness. Then I can, each of them I can disturb differently, and this is a vector perturbation vector delta F. will cause different readouts of the sensors. But if my lighting is constant, this doesn't change between those two perturbations can happen very quickly, within milliseconds. And if general light doesn't change in that period, if I subtract one from the other, this will go away. And then I have just perturbation times light output matrix producing the readout of the sensor. So now I've eliminated ambient light, assuming ambient light is slowly changing and it's global. Affects the whole room. And if I collect this over perturbations over some number of time instants, I can construct a long vector, and from this I can compute A by basically pseudo inverse. So I'm getting back the matrix A from the measurements of multiple perturbations of the signal from different light sources. Now, how to get from A to, from measurement of A, how to get to location, I'm going to skip this. There is some geometry that one can calculate matrix A, light output matrix, based on the knowledge where the sensors and light sources are. And I'm going to skip this. The only thing I would like to say is that it leads to a nice linear equation where delta A is the change in the light transport matrix between the empty state, nobody in the room, and I enter into the room. And this is the change in the amount of light every sensor receives. This is my delta A between A0 and A, and this is caused by the albedo change on the floor. And the question is right now, knowing delta A, which I can compute, I just showed, knowing C matrix is basically depending on where the sensors are. It's just geometry, it's just angles and distances. How to get delta alpha? And this is standard signal processing problem. You want to find delta alpha knowing C and delta A. And we've used ridge regression, standard method. Come on. Okay. So we used ridge regression, where we are minimizing the difference between the two sides, under the standard Euclidean norm on the albedo change. And we can get a reasonable accuracy of where delta alpha is changed. But later on we discovered that we can actually improve this much, much more by, after this first step, identifying where the change took place and applying second time the same ridge regression only within the area of detection from the first part. Just kind of like multi-resolution or hierarchical. You go first coarsely and then you go finely. And this improves right away the outcome. Now let me show only the result and I'll be done. So we did first MATLAB experiments, and then we did Unity 3 simulations, and finally we went to a small scale test bed where students in our capstone design have designed let me show it, little module which included LED light source and a single pixel sensor. So this would be modulated, and this would be receiving the light. And we had like 3x4 array mounted on the ceiling, and we would be modulating light. The problem we discovered, it was too late, students graduated, happily went to work, that LEDs were not powerful enough. And if you place them at the height of about 3.5 meters, there was very little illumination on the floor. Said, okay, all this waste, what do we do? So what we did, we raised the floor. We put a big cardboard and we raised it so that actually we can have effect of this light. And we have placed a variety of objects like big card blocks, cardboard, cut out dark squares of different sizes and try to estimate where they are positioned. Here's our results. So we have been able to, with a passive method that doesn't include this light modulation, our error was significant, about half a meter in a distance of about 2.5 by 2.5 meters. But when we use the active method with the light modulation, we were able to actually reduce the error, and with the method that uses those two regression steps, even lower to about 5 centimeters, regardless of the size. This is a small object, this is a very large object. So in about 2.5 by 2.5 meters, about 5 centimeters, the best we could get location, which we were very happy with. But the question that was more important was, okay, we went through this effort to do this light illumination, light modulation. Does it really help with illumination changes? This was the key point. So we ran another set of experiments where we would our matrix A would be computed in empty and occupied. If it's both in bright and bright, or dark and dark, it should work reasonably well. But we ask, what if empty is in bright, but occupied is in dark, or vice versa? And these are the two scenarios, bright to dark and dark to bright. Here it works well, not surprising. Passive method doesn't work well. Passive method explodes to about 70 centimeters error. But our active method with light illumination doesn't care whether it's bright or dark, in a sense empty and occupied. It still works very well, it gives you about 10 centimeters accuracy. So it shows that there's a robustness due to this light illumination, light modulation. So let me only show you a demo and I'll be finishing the last slide is next. We have actually implemented this in the following year with capstone design, where students have used actual Philips bulbs and built a real system which actually really illuminates from high. And we didn't want to run it at high frequency because you wouldn't be able to see the modulation, so we ran it at a very low frequency. And the student would be literally walking from point to point, and you would see the true location and estimated location. So blue is where he actually moves, and red is the estimate from single pixel measurements on the 3x3 grid. It's not perfect, but it can estimate where the student is going. And in this case, there's no data driven. It's all pure signal processing. The only thing is that we need to capture the data first in empty state, and then occupied state that somebody's in the room. So it's enough at the beginning to capture a room without anybody, and then whenever somebody walks in, it will be estimated. So all this is great. Is it private enough, the question? All of that I talked about single pixel, 2x2, 5x5, 10x10, is it private enough? And the question that we've been recently thinking about, can, from this data that I've collected, single pixels, 6 cameras, 5 cameras, 10x10 pixels, collecting enough data, can one develop algorithms to actually reconstruct the view of a person? And you probably are familiar with the single pixel camera, but not in this sense, but compressed sensing. You know that you can actually do aperture modulation and you can recover. So in this sense, can one do something similar? And we are right now toying with ideas, trying to see whether this can be done. So I'll finish with some final thoughts. So sensors will be around us whether we like it or not. Cameras, I don't know how prevalent they are in India, but in the US, they're in every elevator, the entrance to every building in our department, in our college. So they're everywhere. We don't like sometimes we love them. Everybody loves to carry all possible sensors in their phone. Can you imagine living without GPS right now? I cannot. Here, if I come to Delhi, I would have to have a map or pack of maps in my backpack, and now I just pull out the phone. So we have to live with those sensors. Privacy concerns, we know in a variety of ways. I'm only addressing visual privacy. That's the only thing I'm addressing. As solution, we think that ultra-low resolution sensors can be interesting if they can provide utility without actually disclosing appearance of a person. At very low resolution could be interesting. Bonus, sensors would be simple. Right now, unfortunately, those sensors are very expensive because they're produced in very small quantities, those single pixel sensors. But if they go into every single phone, every single light, they could be probably very inexpensive. The key point that bugs me and my colleagues is the fact that challenge, how do you convince the public that this is not a 4K camera? There's a little lens, there's a little chip. You kind of go, open, oh, this is a single pixel, great. But it's 4K or a single pixel, it was the same. So you put those sensors, how do you convince somebody it's not a 4K 60 frames camera? And I don't have an answer. So with this, thank you very much for your attention, and sorry I overrun a little bit. Thank you.
Yeah, I had a question regarding the third part of that the presentation, where you are checking about the orientation of that person, right? Its basic idea is to get connected to that device by that line, isn't it?
So the idea is this, the assumption is that the person in the room is trying to stream data to some device. It could
Through
be my
that light.
phone or something. Through
That.
the modulated light, which streams data to your device. And I need to find a source, light source, that has direct line of sight. And this is directly related to my orientation. So if I am oriented this way, I cannot really stream from the light behind me because I'm obstructing the line of sight. So that's the idea.
That is correct, but instead of looking for the orientation of the person, let us start detecting the device itself.
You could. If you assume that, for example, the device is, I don't know, Wi-Fi enabled, right? You could figure it out from the signal strength. You could. And in fact, I didn't answer one question. I didn't ask that question even. I've been talking about 1 gigabit per second downlink. We need also an uplink. So with uplink, right now VLC, and they're actually right now being developed standards within IEEE for VLC. And the thought is that perhaps Wi-Fi will be an uplink, because we are really consumers of videos coming down. This is what drives really right now the network traffic. So we really are streaming much more down than uploading. So Wi-Fi is thought as a channel out. But I haven't talked about this much. So in this case, absolutely, you could do through Wi-Fi. And in fact, people have done a lot of interesting work based on EMF analysis. So basically, analysis of the strength of the signal received by the access points from a room where a person is. The person doesn't have to hold the device. The fact that you have, I can see here. There's probably somewhere Wi-Fi access point. Yeah, here it is, right. Only one? Only one, okay. So from the fact that you have Wi-Fi and you have access to actually modulation, you can figure out, not maybe, I don't know about this many people, but people have done work on recognizing where a person is and what the person is actually doing. And the most recent work I've seen, which was to me totally mind-boggling, I think it was a very persuasive scenario, they could figure out the breath rate because of the chest expanding and contracting. This was disturbing EMF enough they could pick up for a single person. So there's at least a couple of companies started out of the University of Washington and MIT who are actually commercializing this technology. And another company has actually demonstrated they can count from the analysis of Wi-Fi signals the number of people in the room. So they can count, for example, right now that there's 20 people, based on analysis, without actually a need for having a device. Just the fact that they are streaming the signal, analyzing what's happening with the strength. I think they need at least 2 access points. And I think when the number grows, they get better accuracy. So there are a variety of ways. And I'm not saying this is the only way, but this is one of the ways. Sure.
Is it safe to assume in this case that, at least based on what you showed here, that all the lights, budgeted lights that you had, were mounted in the ceiling?
So that's not assumption.
Yeah, at least, I mean, the picture showed that none was shown on the walls.
No, we assume that they are not
So if that's the case, if we were to be able to create that environment where that's the case and the cameras are also mounted on the ceiling, have you thought about ways in which you could use a part of the body that's only visible to the ceiling in very well, which is kind of this part of my head, rather than looking at my whole body? Kind of a more constrained shape, maybe some color features there. I don't know how much can one assume, but
we don't really think about this as particular part of the body, because what the sensor receives is a single pixel sensor, so it receives average light from its field of view.
yeah.
So if the camera has, let's say, 60 degrees field of view, it measures average light. And the whole measurement takes into account top of the head, whole body, and also the background, right? So the key problem we have in these sensors is that they have some noise level, which is not minuscule. And the environment contributes the majority of the signal. I am only part of the environment. Light is bouncing off leaves. I mean, I'm gray, this is gray. It's just not that much difference, right? But majority of the light is captured from the environment. So if the environment is noisy, you have, let's say, like a flickering light somewhere. It will disturb a lot. Our difficulty at the moment right now is that the noise level is not good enough for us. And for modulated light, another difficulty we have is that the frame rate of the sensor is not fast enough. We've used the sensors from this company called Taos, which can run up to 30, 35 hertz. It's not good enough for us to illuminate very fast. And there is a Japanese company, I think it's called Hamamatsu. Apparently they have much faster sensors, but as all engineers, I don't know, I mean, I'm saying I'm an engineer, but as most signal processing engineers know, as you reduce integration time, because you want to have high frame rate, sorry, noise goes up. So if I really want to have high frame rate, sorry, I have more noise, right? So we don't know technologically to do it today, we don't know how to do it. We don't have enough fast sensors. But we are using sensors that are extremely tiny. But you could increase the surface of the sensor, right? I don't need to have, micrometer by micrometer, right? I could go millimeter by millimeter and get more light. Nobody makes those sensors. There's no interest, right? Who is going to buy a 1 millimeter sensor? So we're exploring this, and eventually the logic tells me it's going to be very cheap to build it, right? Much cheaper than to build a 4K CMOS sensor. But if nobody builds it, I have to hand build in the lab. It will cost me $1,000 per single sensor, right? So we don't know, how to attack it. And I was happy with the results, but from there to actually building a real system, it's a long way.
Okay, apart from localization or recognition, what else can we solve using this setup?
I'm sorry, again?
Apart from localization or recognition, in this setup, what else can we solve?
I think one could count number of people, potentially. How difficult it is, I don't know. I think like looking at everybody right now, looking from the top, you wouldn't count it probably because you have very similar shirt to the background, to the chair. So it will be difficult. Somebody is distinct, it will be easier. The question is how big accuracy do you need? I think this could be used. We are working right now on people counting in a different project I'm not talking about here, but we're using fisheye cameras. Totally opposite of privacy. We have a 4 megapixel fisheye camera that looks single camera mounted on the ceiling looking at the whole room. But then the question is, I'm diverging a bit from the topic, but I'm living myself and my students in the world of, yeah, privacy is important. On the other hand, do I expect privacy here in this room? We are giving up on privacy very often, right? If I can, mount a camera, will we object? Do we expect privacy? Not in this room. Do I expect privacy in the bathroom at home? I do. So what's the application, right? I think this has applications in, I would see significant applications in, especially in the US and Japan, where society is aging and people want to live in a home much longer themselves. They don't want to go to senior facility. And where do accidents happen most often with seniors? Slipping in a bathroom because of wet floor, reduced mobility. Do you want an HD 4K camera in the bathroom or in a shower or somewhere in that space? No, you don't. Can you mount a couple of single pixel sensors that can actually detect an event without in any way violating privacy of the person? Maybe interesting. This is where I see potential applications. But where I don't expect privacy here, well, give me 10 4K cameras and I can count exactly every single person. We are still grappling with those issues. And the question is also the definition of privacy. We can talk about what does it mean privacy. We've given up on privacy, right? Google knows where I am right now. Maybe it's listening. Google, are you listening? I don't know. But for us, it's visual privacy. Visually, can another person who knows well somebody can from this data recognize the person. and if we claim low resolution, you cannot. Although I hope we cannot, because with deep learning, one never knows. If you have access to the data, you can train something, maybe you will.
So there's a big body of work in the last 5-6 years on activity detection, especially for privacy-related scenarios, and fall detection with radar, because it offers again data that's not, the images don't look like optical images. Are you familiar with
Yes. So radar is, so there is also a flip side that some people would not be very happy that in the home you're going to put another source of EMF, because you need to actively send EMF signal and a receiver in order to detect. Yes, there is some work of this type.
Yeah, but it's the same signal.
Is it safe? I can claim that some people in the US, there are lawsuits where actually schools were prevented from using Wi-Fi. Schools were prevented because parents believed that their children were somehow exposed, and they actually completely forbade using the law. They went to court, and the court acknowledged that, and the school was completely removed Wi-Fi. No Wi-Fi in school. Everything was on Wi-Fi. I'm just saying extreme case, of course, right? But the question is, why would I add another source if I can exploit Wi-Fi, which is everywhere, cell signals, TV signals. There's, if you have a spectrum analyzer, you put it here, and you turn it on, you put an antenna, you will see how much mishmash there is, right? So I would say maybe not active with the radar. I know there's work, but I'm saying, why do I need to put another source if I don't need to?
No, passive radar.
Passive, okay.
You use the existing
Yeah,
signal
yeah.
and just receive.
Yeah. And this is the work out of, I mentioned, and there's other work going. Yeah, this is done too. Yeah, I agree totally. And it's possible that they may work in conjunction. Because there are situations when this technology doesn't work well, and the situations where we have disruption, and the EMF won't work very well. So, yeah.
Okay, so let's thank the speaker.
Can I take a picture of the, sometimes I take a picture just to have, to remember.
It's privacy violation.
I don't mind.
I'm going to keep it only for my own records. Don't even give to IEEE SPS. Just as my memory, thank you.
So now, Prof. Would you like to begin?
Oh, thank you very much.
Thank you so much for coming here.
I enjoyed very much coming to the campus, and I was, some people say I'm stupid or something, but I love to walk in every city I go to. So I took metro, I walked, I of course took the wrong gate, I went all around and saw the cows and dogs and everything. But what's amazing is that you walk out of those little houses and you go to the gate. What is this? And it's like a huge campus in the middle of residential area, which is interesting. It is, definitely. It's an experience. So thank you for inviting me, and thank you for spending an hour and 15 minutes with me.